The first level of organization in living things is chemistry, so let's see how chemistry comes alive. Matter is anything that takes up space and has mass. It exists in three forms. Solids have a definite shape, liquids take the shape of their container, and gases fill their container. The other concept of chemistry is energy. Energy doesn't have any mass, but it's measured by its effects on matter. It can make matter do things. Energy is the capacity to do work, and there are two types of energy. Kinetic energy is the energy of motion. When something is moving, it has kinetic energy. Potential energy is stored energy. Energy is stored and can be used at a later date. Batteries have potential energy when they're not in something, but if they're in a flashlight and you turn the flashlight on, you then have kinetic energy because then molecules are moving. There are several forms of energy. Chemical energy in living things is stored in the ATP molecule. This is energy that's stored in chemical bonds. Electrical energy is the energy of charged particles. This is ions in motion. Mechanical energy is the energy of moving matter. And radiant energy is energy that travels in waves or rays. These are your electromagnetic waves, things like ultraviolet light, X-rays, and visible light. Energy cannot be created or destroyed. It can change form. Chemical energy can become mechanical energy, for example. However, whenever energy changes form, it's not efficient. If you want chemical energy to become mechanical energy, you usually get some energy in a form you don't really want. For example, gasoline in your engine turns the wheels on your car. Gasoline would be chemical energy. Turning the wheels on the car would be mechanical energy. But when you take that chemical energy and turn it into mechanical energy, you also get a fair amount of heat. That's a form of radiant energy, and it's a form of energy you didn't really want. Atoms, elements, and compounds are the next topic of discussion, and you're probably going to hear more about this than you ever wanted to know. Elements are substances that can't be broken down by ordinary means. They make up all matter. Elements are composed of atoms. Now, atoms are composed of protons. Protons have a positive charge and they have a mass of 1. Neutrons have no charge, they're neutral, and they also have a mass of 1. And electrons have a negative charge, and they have no mass to speak of. We think of electrons as being energy. Protons and neutrons are found in the center of the atom, an area called the nucleus, and electrons travel in orbitals around the nucleus. This is the periodic table of elements. Each square has a system of letters in it. These are the various chemical symbols. Also, there are two numbers. This number at the top is different in every single box. And it's a whole number. And then we have some numbers that are not whole numbers that are down here. Here are some examples of atoms. You see the protons and the neutrons in the nucleus, and you see the electrons orbiting around. Atoms are electrically neutral. There are the same number of positive charges as there are negative charges. Since the protons have the positive charge and the electrons have the negative charge, the number of protons always equals the number of electrons. Here in this atom we have 1 proton and 1 electron. This is hydrogen. Here we have 2 protons and 2 neutrons. They're in the nucleus. Since we have 2 protons, we have 2 electrons. And here we have 3 protons and 3 electrons. This particular atom happens to have 4 neutrons. The number of protons and neutrons does not have to be the same. This is a section from the periodic table. Because the number of protons equals the number of electrons, positive charges equal negative charges, atoms are always electrically neutral. Now the atomic number, this number in the top of the box, is the number of protons. So whenever we have this number, we know how many protons there are, and because protons have to equal electrons, we also know how many electrons there are. The atomic mass is the whole mass of the atom, and since protons and neutrons are the only things that have mass, the atomic mass number is this number at the bottom. And it's the average of the weights of all forms of an element. Now there are different forms of the same element. Carbon typically has 6 protons, 6 neutrons, and 6 electrons. However, there are some atoms of carbon that have more than 6 neutrons. These alternate forms of an element are known as isotopes. We always have to have the same number of protons because that's what determines what the element is. But different atoms can have different numbers of neutrons. That is what gives us a different atomic mass. Some isotopes, the one known as radioisotopes, are unstable. They give off subatomic particles. This is radiation. They can give off alpha, beta, or gamma rays. Some forms of radiation, particularly the gamma radiation, damages tissues. Now, we have used this form of radiation to treat cancer, but if you're exposed to this form of radiation and it's not focused on a cancer cell, it can actually cause cancer. Even though there are 116 elements known, the elements of life are relatively few in number. 96% of living things are composed of 4 atoms: carbon with the chemical symbol C, hydrogen with the chemical symbol H, oxygen O, nitrogen N. The trace elements, which make up almost all of the rest of living things, 3.9%, are sodium, Na is its chemical symbol, potassium, K, chloride, Cl, calcium, Ca, phosphorus, P, iron, Fe, iodine, I, sulfur, S, and magnesium, Mg. These are the elements that you need to know the chemical symbols for. To help you remember which elements are important to life, you can remember C. Hopkins Cafe, where the manager uses lots of salt. Carbon, hydrogen, oxygen, nitrogen are the major 4. Then we have phosphorus, iodine, potassium, sulfur, calcium, iron, magnesium, sodium, and chloride. Those are all of the elements that are primarily important to living things. Compounds are substances that are composed of 2 or more kinds of atoms that are chemically bonded together. Some examples are methane, CH4, we have carbon and hydrogen, and we know we have 4 hydrogen atoms in this compound because of the subscript 4 right here, or sodium chloride, table salt, made up of sodium and chloride. A molecule is 2 or more atoms that are held together by chemical bonds. Now, a molecule is the smallest component of a compound. H2O is water. It is a compound because there are 2 different elements involved. All of these are compounds and they all represent molecules. But not all molecules are compounds. Sometimes elements chemically combine with each other. So you can have O2. We know that this is 2 atoms because there's a subscript 2, and that means that that's a molecule, because a molecule is just 2 or more atoms, not different atoms, just 2 or more atoms. Compounds are 2 or more kinds of atoms. Mixtures are composed of 2 or more components that have been physically intermixed. The components do not chemically bond to each other so that they can be separated by physical means. You can dissolve sugar in water. That's a mixture. If you had the right equipment, you could evaporate the water off and recapture it as water, and the sugar crystals would be left behind. There are 3 types of mixtures: solutions, colloids, and suspensions. Solutions are homogeneous and transparent. The solute is the smaller quantity. It's dissolved in the medium. And the solvent is the larger quantity. This is the dissolving medium. In life forms, water is always the solvent. Your body fluids and plasma are examples of solutions. Colloids are heterogeneous. They have solids with liquids. The particles are larger particles, but they stay suspended. They don't settle out. They give you kind of a milky appearance. We sometimes talk about sol-gel transformation. This is like you see in Jell-O. At certain temperatures, Jell-O is solid. At other temperatures, it becomes more liquid. Cytoplasm is an example of a colloid in living things. Suspensions are also heterogeneous, but here the particles are large and visible, and unless the suspension is in constant movement, the particles will settle out. Blood blood cells suspended in plasma is an example of this. Unless the blood is being circulated and pumped through the body, if you draw blood out of the body and put it in a test tube, you will see the blood cells settle to the bottom of the test tube. That is a suspension. So here you see solutions, very, very tiny particles, evenly distributed, like mineral water. In colloids, the solute particles are larger. They tend to scatter light, which gives you that milky appearance, but the particles don't settle out, like in Jell-O. But in a suspension, the solute particles are very large. They may or may not scatter light, but if you do not have this in constant motion, then you will see the particles settle out. So the difference between mixtures and compounds. In mixtures, there's no chemical bonding between the components. We can take the components apart by physical means, such as straining or filtering. They may be heterogeneous, that is, unevenly mixed, or homogeneous, very evenly mixed. In compounds, there's chemical bonding between the components. We can only separate the components by breaking these chemical bonds. All compounds are homogeneous. Since chemical bonds are involved in compounds, exactly what is a chemical bond? Well, this is when electrons interact between the atoms. Electrons want to have their outer electron shell full of electrons. We sometimes refer to this outer shell as the valence shell. The first shell of every atom will only hold 2 electrons, and then it's full. But all of the other shells hold 8 electrons. This is sometimes referred to as the octet rule. Since electrons are basically energy, whenever we make a chemical bond, it requires energy to form it, but whenever we break a chemical bond, we get that energy back. Atoms that are chemically inert have a full outer shell. Here is helium. That first shell is full with 2, so this will not react with anything. This is neon. Its second shell is full with 8. These 2 atoms have no need to interact with any other atom. Helium can be used in balloons and it will not burn. Burning is a chemical reaction, and helium, because it is inert, will not involve itself in chemical reactions. The reactive elements have outer shells that are not full. Hydrogen, for example, is still looking for 1 electron. It needs 2 to fill that shell. Carbon needs 4 more to fill its outer shell. Oxygen needs 2 more electrons. And sodium would need a total of 7 electrons to fill its outer shell. There are 3 types of chemical bonds. Ionic bonds and covalent bonds are very strong chemical bonds. Hydrogen bonds are weak attractive forces between certain molecules. In ionic bonding, electrons are transferred from one atom to another. This means that atoms either lose electrons or gain electrons. Now, once they have lost electrons, they have fewer negative charges. If they gain electrons, they have more negative charges. They are no longer electronically equal. We call these particles ions, these charged particles, because the electron number and the proton number no longer match. If something picks up electrons, it has extra negative charges. Those are negatively charged ions known as anions. If they lose electrons, they have more protons than they have electrons, so they're going to have a positive charge. These are called cations. Now, to help you remember this, you can think of anion as standing for a negative ion, or cations, you can see the plus sign right there in the middle of the word. Things that ionically bond dissociate in solution. That is, they separate from each other. They stay in the same orientation, but water molecules slip between them. Solutions like this can conduct electricity, so things that are ionically bonded are known as electrolytes. Ionic compounds are known as salts, acids, and bases. As we look at the formation of an ionic bond, remember sodium only has 1 electron in its outer shell. This electron is very easily enticed away by an electron-hungry atom. Chloride is looking for exactly 1 electron. So when these come in close proximity, sodium loses its electron and becomes a positively charged cation, and chloride picks up that electron and becomes a negatively charged anion. While these look like they have full outer shells, because they are charged particles, opposites attract, and so these two stick together because of the difference in charge. In covalent bonds, atoms share electrons. Now they can share 2 electrons, that's known as a single bond. They may share 4 electrons, that's a double bond, and they may even share as many as 6 electrons, that's known as a triple bond. There are 2 types of covalent bonds. In nonpolar covalent bonds, the electrons are evenly distributed in the molecule. We say there is equal sharing of the electrons among all of the atoms involved. In a polar covalent bond, the electrons are unevenly distributed. There are areas in the molecule where there are more positive charges or more negative charges. We say that this is unequal sharing. This gives the molecule an area of negativity. In a single covalent bond, the atoms are sharing 1 electron. So carbon is looking for 4 electrons. 4 hydrogens can each share 1 electron, and we can have single bonds, and these are covalent bonds. A double covalent bond occurs when a pair of electrons is shared. 2 electrons are shared. Now here we see 2 oxygen atoms combining to form an oxygen molecule. In a triple covalent bond, we have 6 electrons total shared, 3 pair. And this is another example of a molecule that's not a compound. Here, 2 nitrogen atoms are going to share their 6 electrons. We'll have a triple bond between them, and we'll have a molecule of nitrogen. If the electrons are equally shared among all of the atoms, then you have a nonpolar bond. Carbon dioxide is an example of this. But if the electrons are unevenly distributed, then you have a polar covalent bond. This is what occurs in water. Here you see the oxygen molecule, and you'll have to imagine that there are electrons out here that are sort of hanging out by themselves. And these hydrogen ions, their protons are sort of hanging out over here by themselves. So we have a slightly negative area of the molecule and a couple of slightly positive areas of the molecule. So as we look at the strength of the bonds, in ionic bonds we have a complete transfer of electrons. We get separate ions that are charged particles like sodium and chloride, and they stick together because of the difference in charge. In a polar covalent bond, we're sharing electrons, but it's an unequal sharing. This means that we're going to have a polar molecule, a molecule with a slightly negative area and a slightly positive area. This would be like water. And in nonpolar covalent bonds, we're still sharing electrons because it's covalent bonding, but this time it's equal sharing. The charges are balanced among the atoms, as in carbon dioxide. Hydrogen bonds, our third bond type, are not true bonds. They're really weak chemical attractions between polar molecules. This is what holds water together. It holds DNA together. Now, because it takes energy to break bonds, these weak hydrogen bonds are very important to living things. It allows some molecules to be closely associated to each other, but if we need to separate them, it does not require a lot of energy. Here you see water molecules, and the little dotted lines indicate the hydrogen bonds. Notice that the slightly positive ends are attracted to the slightly negative ends of each water molecule. This gives water the property of cohesiveness. If you pour water on a surface, you'll notice that it beads up. That's because the water molecules are held to each other. The water doesn't sheet out, but rather holds itself together. Chemical reactions can be depicted by chemical equations. These are simply interactions between various molecules and atoms. When we write a chemical equation, we have what are called the reactants, that is the molecules or atoms we're working with, and we have the products, what we get when we're finished. We always use molecular formulas. We use those chemical symbols. Subscripts tell us how many atoms of each kind are in each molecule. Sodium plus chloride gives you sodium chloride. A lot of times you'll see the two-headed arrow because most chemical reactions in living things are reversible. Under certain conditions they go one way, under other conditions they go another way. Because energy is involved in chemical reactions, we have exergonic reactions. These are the kinds of reactions that release energy. This typically results when bonds are broken. Inorganic reactions require energy. This is the kind of reaction that's involved when we're forming new bonds. There are three basic types of chemical reactions. Synthesis is the building of molecules. So sodium plus chloride, making sodium chloride, is a synthesis type reaction. Decomposition reactions are breaking kinds of reactions. We take glucose, it breaks down to carbon dioxide and water. And then we can have exchange reactions. Here, the reactants sort of rearrange themselves and we get different products. So that sodium hydroxide and hydrochloric acid, when mixed together, will give you sodium chloride and water. Now, synthesis reactions are going to require energy, so these are endergonic. Decomposition reactions are going to give off energy, so they are exergonic. And exchange reactions, it really depends on what's going on here. You're breaking bonds and you're making new bonds. So breaking bonds will give up energy, making new bonds will require energy. What's left over at the end? Sometimes you've used more energy than you made, sometimes you make more energy than you use. Chemical reactions, their rate, how fast they occur, are affected by several things. One is temperature. The higher the temperature, up to a point, the greater the rate of the reaction. The higher the concentration of the reactants, the higher the rate of the reaction. Small particles move faster, and since chemical reactions rely on molecules and atoms bumping into each other, small particles move faster. That gives you a higher rate. And finally, most importantly in living things, the presence of catalysts. Catalysts are chemicals that can increase the rate of a reaction without themselves being either part of the reactants or the product. They go in and they come out exactly the same way. In living things, enzymes are our biological catalysts.